Welcome back to this online lecture on quantum computation. So, if you haven't watched the previous video about quantum superposition and quantum entanglement, please watch that first before you come here. So, before we go to quantum computation, let us understand a few basic definitions regarding a computer. A computer is a machine that can be programmed to carry out logical operations. By a program, we mean it is a set of instructions for the computer to execute. And by computation, we mean it is any type of well-defined calculation. An algorithm is a finite sequence of instructions typically used to perform a computation. Computation is done by digital circuits, which consist of logical gates. Any task done on the computer is in principle a mathematical operation. Now, classical computers, those computers which simulates mathematical operations on classical systems, which obey laws of classical physics. The examples are all around us. The desktops, laptops, smartphones, tablets, our smartwatches, all these are part of classical computers because the mathematical operations are simulated by classical systems. A binary digit or bit for short. So, how information is stored in classical computers? In classical computers, the information is stored in the form of binary digits or bits for short. Binary digits are numbers that consist only of two symbols, namely 0 and 1. If there is only one digit, then it is 1 bit, 0 1. If there are two digits, then it is 2 bits, 0 0, 0 1, 1 0, 1 1. Likewise, we can have multiple bits. Example. Now, if you the English alphabets can be coded using 5 bits. For example, A can be called as 0 0 0 0 1. B can be coded as 0 0 0 1 0. C can be coded as 0 0 0 1 1, and so on till Z can be coded as 1 1 0 1 0. And numbers, for example, the decimals 0 1 2 3 can be coded as 0 for 0, 1 for 1, 2 can be coded as 1 0, 3 can be coded as 1 1, 4 can be coded as 1 0 0, and so on. So any information, any piece of information can be coded in binary digits in 0 and 1. How is information of an image stored? Here you see the image of a bug. The image consists of large number of pixels. Each pixel has a specific color and each color is encoded in binary. More the number of pixels, the more the information it contains, higher is its size. Information is physical. Information is stored on materials which have small cells. The cells can be magnetized in downward or upward direction. We assign 0 for one direction and 1 for the other. Here you can see the image where there is a read head where it reads the information on the disk, whether it is spin down or spin up. If it is spin down, it is 0. If it is spin up, it is 1. And there is a write head which magnetizes the cell in either spin up or spin down. So the operations can be carried out using logical gates, and these are some of the familiar classical logical gates. The AND gate, for example, it has two inputs A and B. If the two inputs A and B are 0, then the output is also defined to be 0. If A is 0 and B is 1, the output is still 0. If A is 1 and B is 0, the output is still 0. The output is 1 only if both the inputs are 1. So even if one of the outputs is 0, the output is 0. In the OR gate, when both are 0, only then the output is 0. If one of them is 1, then the output is 1. and the NOT gate is just the negation, where you input 1 and the output is 0, and the other way round. Now let us come to a quantum computer. So those computers which simulates mathematical operations on quantum systems which obey laws of quantum physics. So this is a processor developed by the quantum processor developed by an IBM. So quantum computers are not still commercially available to anyone. They are only kept in facilities such as IBM or Google and meant for research purposes. Why do we need quantum computers when we have classical? What advantages do they offer? There are certain class of problems which cannot be solved by classical computers. For example, given to uh, given to any numbers, a classical computer can multiply them and give the result. But given a large number, a classical computer takes exponential time, very large time to factorize them. Factorizing a very large number is not possible in a classical computer, however advanced it may be. The problem of factorizing a large number is possible in a quantum computer using a quantum algorithm called Shor's factorizing algorithm. The computation time is less in a quantum computer for factorizing compared to that of a classical computer. One more example, suppose there are n objects. The problem is to search for one object out of the n objects. The best algorithm on classical computer will require n steps in the algorithm to search for the object, while it takes only root n steps. When you take the square root of something, it is lower than before. So the root n steps to search for the object in a quantum computer. This is called Grover's algorithm. Computation is faster in a quantum computer. Computations take an exponential time on classical computer can be solved in a quantum computer in polynomial time. Why a quantum computer computes faster? This is because quantum computers carry two unique features which are absent in classical computers: quantum superposition and quantum entanglement. They are present only for quantum systems. Because of these two features, quantum computation is more powerful than a classical computation. Now let us understand what is a quantum bit or qubit. While a single classical bit can be 0 or 1, 0 or 1, a single quantum bit, qubit for short, is a superposition state of 0 and 1. It is not 0 or 1. It is in both the states simultaneously. A qubit is simultaneously in 0 and 1 state. A single qubit is a quantum state and is written as ket psi is equal to A, ket 0 plus B, ket 1. Here A and B are complex numbers in general. So after measurement, the superposition is destroyed and the qubit is found to be in either the state 0 with probability modulus A squared, or it is found in the state 1 with modulus B squared. And since the modulus A squared and modulus B squared are probabilities, we require them to be normalized. The sum of probabilities must be equal to 1. From normalization condition, we have modulus A squared plus modulus B squared is equal to 1. The states 0 and 1, ket 0 and ket 1, are called computational basis states. If there is equal chance of finding the qubit in either ket 0 or ket 1 after the measurement, then A and B take values 1 by root 2. 1 by root 2 squared is the probability of finding the qubit in the state 0 or 1. Clearly, it is normalized. 1 by 2 plus 1 by 2 is 1. Now, how do you physically realize a qubit? We have given three examples here. Say the ground state and the excited state of an atom can be realized as a single qubit. Ket 0 for ground state, ket 1 for excited state. Spin state of an atom can be realized as a single qubit. Ket 0 for spin up, ket 1 for spin down. The polarization state of a photon can be realized as a single qubit. Ket 0 for vertical polarization, ket 1 for horizontal polarization. You can also have multiple qubits. So classically, two bit states can be 00, 01, 10, or 11. Quantum 2-bit states are superposition states of 00, 01, 10, and 11. And the 2-qubit state can be written as ket psi is equal to A, ket 0 plus B, ket 0 ket 1 plus C, ket 1 ket 0 plus D, ket 1 ket 1. After measurement, the superposition is destroyed and the qubit is found to be in one of the states. It is the probability of finding it in the state 00 is mod a squared, probability of finding it in the state 01 is mod b square, in 10 is mod c square, in state 11 is mod d squared. And again we have the normalization condition. The sum of the probabilities must be equal to 0. Mod a square plus mod b square plus mod c square plus mod d square has to be equal to 1.